The general power rule that we've been discussing is really just a special case of a more powerful rule called the chain rule. And what we're going to do now is talk about generalizing the general power rule to the overall chain rule. Alright, so let's take a look at this function y equals the sixth power of 3x plus 1. We're asked to write that as a composition of functions. So here's the way I'm going to do that. I'm going to give the inside function its own name. I'm going to call the inside function u. So u equals 3x plus 1. Then y is u to the sixth. Now that doesn't look quite like the f of g of x notation we've used before, but it is the same kind of thing. So now we're asked to differentiate y equals the sixth power of 3x plus 1 and compare the factors in the derivative to the inner and outer functions you found above. What's all this saying? Well, first of all, let's differentiate y equals the sixth power of 3x plus 1. Alright, so y prime would be 6 times 3x plus 1 to the fifth times 3. Now I'm going to do something that might surprise you. I'm going to replace this 3x plus 1 inside the parentheses with u. So this is the same thing as 6u to the fifth times 3. Now let's think about where all this came from. First of all, where did this 3 come from? Well, the 3 is the derivative of the inner function, the inside function. The 3 is the derivative of u. So 3 is actually the derivative of u with respect to x. U depends on x, and so x is the independent variable and u is the dependent variable. So that's what du over dx is. Now what about this 6u to the fifth? Well, actually that looks a lot like the derivative of this, doesn't it? In fact, that's exactly what it is. But again, using this Leibniz notation, now we've got y expressed as a function of u. If we're going to call 6u to the fifth the derivative of u to the sixth, this would actually be the derivative of y with respect to u, right? If we're differentiating this function, the independent variable here is u, and so we would say that dy over du is 6u to the fifth. So going down here, and here's the reason for doing this. Going down here to the derivative, this is 6u to the fifth. That is dy du. 3 is du over dx. And this y prime here, that was the derivative of y with respect to x, since we were, in this case, we were working with y as a function of x. And so what we've got here is a statement of the general power rule. If y is a function of u and u is a function of x, so if y is a function of u, and I'll just write it like this. F of u, and u is a function of x, and I'll just write that as g of x. Then the derivative of y with respect to x, let me back out just a little bit. Then dy over dx, the derivative of y with respect to x, is dy over du times du over dx. All right. So dy over dx, here was our y. When we came up with this derivative, that was dy over dx. Now, that is made up of dy du. This part can be rewritten as 6u to the 5th, which would be dy du. And then this part, the 3, is the derivative of u with respect to x. This is the general chain rule. I mean, this is the generalization of the general power rule. This is the chain rule. Let's do an example after we say this. Another way to write the chain rule is this way. If y equals f of g of x, now the g of x is playing the role of the u in what we just said. The g of x is playing the role of u. So remember that what we had was that the derivative of y with respect to x was the derivative of y with respect to u, that's this part, times the derivative of u with respect to x, that's this part. Sometimes we say the following. The derivative found using the chain rule can also be expressed as the derivative of the inside function evaluated at the inside function times the derivative of the inside function. Let's take a look at an example. Here we've got y equals sine of x squared, and I want to think of this firstly by rewriting as a composition of functions, sine of u and whatever u is. So y is the sine of u, where u is equal to x squared. Alright, so dy dx is dy over du times du over dx. And a way to help you remember this, there's a little mnemonic device. You can think of the du's as canceling. If you've got dy times dy over du times du over dx, and these were fractions, you could cancel out the du's and get dy over dx. In reality, they're not quite fractions. They're really limits of fractions, but thinking of them as fractions is actually kind of a powerful tool, and it is often perfectly fine to do that. Anyway, let's see if we can figure out what this derivative is. So we need the derivative of y with respect to u. Take the derivative of this part, and that would be cosine of u. And then we need to multiply that by du dx, the derivative of u with respect to x. That would be 2x. Now, you would expect the answer to be written only in terms of only in terms of x without any u's. So let's go ahead and replace this u with x squared. And I'm going to rearrange this while I'm at it. We're going to get 2x times the cosine of x squared. Now, that's a lot of writing, and it was time consuming, And I think generally people do not go to all that much trouble. The way that they usually differentiate something like this, like the sine of x squared, and I'm going to refocus. The way they usually differentiate something like this is they think of the derivative of the outside function evaluated at the inside function times the derivative of the inside function, which is just what I have right here. So let's think of it in those terms. We want the derivative of the outside function. Well, what's the outside function? Well, that's the sine, and then the x squared is the inside function. So I'm just using O and I to stand for outside and inside. So you want the derivative of the outside function. Well, the derivative of the sine is the cosine. But cosine of what? Well, it's the derivative of the... I have a mistake. That should say outside. The derivative of the outside function evaluated at the inside function. So that means put the inside function in here. Do not differentiate it yet. But then you multiply this by the derivative of the inside function, and the inside function is x squared, so the derivative would be 2x. And that's the same thing we're getting here. 2x times the cosine of x squared. So I think in general that's what we want to do. Let's see if we can do a couple more examples. In number 2, we've got y equals the secant of 3x plus 1. So the outside function is the secant and the inside function is 3x plus 1. So we want the derivative of the outside function. Well, I hope you remember what the derivative of the secant is. It's the secant tangent. Well, secant of x times, secant of what times the tangent of what? Well, this function is evaluated at the inside function. That's really just sort of a loose way of saying we keep the inside function in there. And now we need to multiply by the derivative of the inside function. All right, let's do one more. This one involves the chain rule and the product rule. So here's A, here's B. F prime of x is going to be A times B prime. We need the derivative of the sine of 2x. That'll be the cosine of 2x times the derivative of the inside function, which is 2, plus the derivative of x is 1 times sine of 2x. And that gives us 2x cosine of 2x plus sine of 2x.